In the previous chapter, we talked about applications of vibrations in continuous systems. And in the chapter prior to that, chapter 9, we talked about approximate methods for multiple degree of freedom systems. So now we're going to consider approximate methods for continuous systems. And again, revisit this Rayleigh's quotient in particular. So just to look at the outline of the chapter, we're going to mostly focus on application to lateral vibrations of beams. And to do that, we'll look at kinetic energy, potential energy, and then study Rayleigh's quotient for lateral vibrations in beams, and extensions to Rayleigh's quotient or Rayleigh's method for beams. So we examined several types of continuous systems in chapter 10, and for simple geometries, we were able to find analytical solutions. This is really only possible in the simplest situations, as materials with varying densities, cross-sectional areas, elastic properties, etc., along with complex boundary conditions, cannot be easily described with analytical solutions. So approximate methods are needed for these complex cases. For continuous systems, Rayleigh's method is well suited for approximate solutions. So if you recall, for discrete systems, Rayleigh's quotient was expressed as our estimate of p squared is equal to our assumed mode shape phi, so phi transpose k phi divided by phi transpose m phi, where k was the stiffness matrix and m was the mass matrix for the system. And we used a trial vector to get an estimate for the fundamental natural frequency. So Rayleigh's quotient was based on the fact that for a conservative system with potential energy equals 0 at the equilibrium position, that the maximum kinetic energy is equal to the maximum potential energy, or Tmax is equal to Umax. So we can also apply this result to continuous systems when all the displacements are at their maximum at a given time and all the velocities are at a maximum at a different given time. So the displacement and velocity of the masses in a discrete system can be replaced by infinitesimal mass elements in a continuous system. So the displacements and velocities are given by, or through this displacement function, u of x and t. So the procedure to find the approximate natural frequencies for a displacement function of u of x and t is first estimate the fundamental mode shape. So that's like our assumed kind of trial vector, or in this case, assumed mode shape function. Then assume simple simultaneous harmonic motion of the form u of x and t is equal to some function of u, so our mode shape u of x, some function of x, times this harmonic motion sine pt plus phi. And then we find the maximum potential energy U max, find the maximum kinetic energy T max, and set U max equals T max and solve for P. Now, to get an accurate value for the natural frequency, it is vital to get an assumed mode shape that satisfies the geometric boundary conditions of the problem. It doesn't need to satisfy all of the boundary conditions, but it does need to satisfy at least the geometric boundary conditions, and it should satisfy as many boundary conditions as possible. Without appropriate boundary conditions, we are effectively solving for a different system. If we do have appropriate mode shape, then the frequency we calculate is an upper bound of the lowest natural frequency. So to use Rayleigh's method for beams with lateral motion, we need to determine the potential and kinetic energy with specific vibration mode shapes. The potential energy is stored in a beam as elastic energy due to the strain in the material. In most cases, the energy stored due to bending is much greater than the energy stored due to the axial or shear forces, so we only focus on the bending strain energy as the potential energy of the system. So an initially straight beam is deformed into an arbitrary shape, which we can call y of x and t, and of course assuming small displacements as usual. So we have something like this, some beam that's in its deformed configuration. And then we can look at an infinitesimal element of this beam in its deformed configuration with a length dx. And the bending is described by this angle d phi, and we've got this radius of curvature r. So the element has a radius of curvature r, which is related to the angle as d phi is equal to dx over r. And for an elastic beam, the bending moment is equal to EI times 1 over r. Now, if we consider the infinitesimal work done to deform an initially straight beam element at equilibrium to one with an included angle d phi, as shown on the previous slide, then the work is dW is equal to 1/2 m d phi, which is equal to the area under the m phi graph, as shown here. The work on the elastic beam is equal to the strain energy stored in the element, which we call du. So we get that du is equal to dW, which again was equal to 1/2 m d phi. And now if we substitute our values for m and d phi that we talked about, then we can see that we have du is equal to 1/2 EI 1 over r times dx over r, or du is equal to 1/2 EI 1 over r squared dx. And for small deflections, 1 over r, so again, the r was the arc length, or sorry, the radius of curvature. 1 over r is approximately d2y by dx squared. So then this becomes du is 1/2 EI d2y by dx squared dx. And this is the stored strain energy in the element. To get the total energy stored in the beam, we can integrate over the length of the beam. So U, which is the total energy of the beam, is the integral over the beam of du, which is the integral from 0 to L of 1 over 2 EI d2y by dx squared dx. And we make the usual assumption that the beam motion has the form y of x, and t is this function y of x times the harmonic motion sine pt plus phi. So then taking the partial derivative d2y by dx squared is the total derivative d2 capital Y by dx squared times sine pt plus phi. And our expression becomes u is equal to 1/2 the integral from 0 to L of d2y by dx squared sine pt plus phi, all of that squared dx. And the maximum strain energy occurs when this sine term, sine pt plus phi, is equal to plus or minus 1. And this occurs at the same time for all points on the beam. So if we use this with the maximum strain energy, then we can find that U max is equal to 1/2 the integral 0 to L of EI d2y by dx squared dx. And this represents the maximum strain energy stored for the assumed mode shape of y of x. And we can also make note of the fact that since m is equal to, or the bending moment is equal to EI d2y by dx squared, we could write this as U max as 1/2 times the integral from 0 to L of m squared of x over EI squared dx. And this may be useful in some situations. Now to get the kinetic energy, we consider the infinitesimal element again. And if we ignore any rotational energy and consider only the translational energy, which is basically the Euler beam theory, then the kinetic energy in this element is dt is equal to 1/2 dmv squared, where dm is the density times the cross-sectional area times the length, so rho a dx. And the velocity of this element is partial y by partial t. And using our typical assumption for beam motion, y of x and t is equal to y of x times sine pt plus phi, we can find partial y by partial t is just y of x times p cosine pt plus phi. Now we combine these results on the previous slide. The kinetic energy of the beam becomes dt is equal to 1/2 rho a times y of x p cosine pt plus phi, all of this term squared dx. So the total kinetic energy of the beam is found by integrating over the beam. So again, it's the same expression, just integrated from 0 to L. And this is a maximum when cosine pt plus phi is equal to plus or minus 1, which again occurs at the same time for all the points on the beam. So the maximum kinetic energy, T max, is 1/2 p squared times the integral from 0 to L, rho a y of x squared dx. And for a conservative system, T max is equal to U max. So this is assuming that the maximum kinetic energy, basically that there's zero potential energy at the equilibrium position, and the kinetic energy is a maximum at the equilibrium position. So if this is the case, then T max equals U max, and we can use basically set these 11.11 and 11.8 equal to each other to get this expression here, and we can rearrange and solve for p squared, and this gives us an estimate of our natural frequency associated with our assumed mode shape. And this is called Rayleigh's quotient for beams, where y of x is an assumed mode shape for the beam. And if this assumed mode shape satisfies the boundary conditions, the geometric boundary conditions in particular, then this defines the upper bound on the lowest natural frequency. Now we can extend Rayleigh's quotient, or Rayleigh's method, by considering some additional elements in the system. So Rayleigh's quotient for beams, given by 11.12, was found by considering the ratio of the maximum potential and kinetic energies in the system. And we can extend this principle to multiple masses and springs in a single system. So for example, if we have a system like this where we've got a beam with additional extra masses, so M1 here and M2 here, and additional supports like a spring stiffness K1 and another spring K2. So to extend Rayleigh's quotient, we need to determine the potential and kinetic energy of this full combined system. So first, to determine the potential energy stored in the system, for an assumed mode shape y of x, we include the potential energy stored in the springs. So the energy stored in the springs is just 1/2 k1 y of a squared, where k1 is at a distance a, or at a position A, plus 1/2 k2 y of b squared, where k2 is at this position B. So yeah, y of A and y of B are deflection of the beam at A and B respectively. And the maximum stored energy is then just the combination of this, the sum of the energy stored in each of the elements. So it's the energy stored in the beam, 1/2 the integral of 0 to L ei d2y by dx squared dx, plus 1/2 k y of A squared plus 1/2 k2 y of B squared. So the extra kinetic energy of the masses is 1/2 m1 v1 squared plus 1/2 m2 v2 squared, where v1 is partial y by partial t at x is equal to c, which is the location of the mass m1, and v2 is partial y by partial t at x is equal to d, which was the location of m2. And we've already seen that this partial y by partial t is equal to v of x p cosine pt plus phi. So the speeds then become v1 is just y of c p cosine pt plus phi, and v2 is y of d p cosine pt plus phi. So just evaluating this at x is equal to c and x is equal to d. Because these are maximum at cosine pt plus phi equals 1, the maximum additional kinetic energy is then 1/2 m1 p squared y of c squared plus 1/2 m2 p squared y of d squared. So adding this extra kinetic energy to that of the beam gives our T max is 1/2 p squared integral from 0 to L rho a y of x squared dx. So that's the kinetic energy of the beam plus the kinetic energy of the masses, 1/2 m1 p squared c y of c squared plus 1/2 m2 p squared y of d squared. And now if we set our T max is equal to our U max, we get this expression here, and we can cancel out the 1/2s and rearrange to solve for p squared. So our estimate of p squared now is contains these additional elements for the additional springs and additional masses. And this can be generalized to a beam with any number, R number of masses and S number of springs, as shown here, where we can write this as the sum of over all the springs of Ki y xi squared, and the sum over all the masses of M as mj y of xj squared.